Good evening, everyone. Thank you so much for joining us tonight. My name is Kate Bruns, and on behalf of Harvard Bookstore, the Harvard University Division of Science, and the Cabot Science Library, I am very pleased to welcome you to our program tonight with Felice Frankel, discussing her latest book, Picturing Science and Engineering. In just a moment, I will turn you over to Professor Alyssa Goodman of the Harvard Astronomy Department, who will introduce the program this evening. But first, I'd just like to take a quick moment to tell you about this Science Book Talk series, which is a collaboration between the Harvard Division of Science, the Cabot Science Library, and Harvard Bookstore. The series features talks throughout the academic year by the authors of recently published books on a variety of science-related topics. Next up, on May 8th, we will welcome President of the Royal Society and Nobel Prize-winning biologist Venki Ramakrishnan for a discussion of his latest book, Gene Machine: The Race to Decipher the Secrets of the Ribosome. So now I will turn things over to Professor Alyssa Goodman.
Good evening, everyone. Thank you for coming. I know that you probably already know that you're in store for a treat. And I should tell you that I don't usually make notes to introduce friends, but I did this because I wanted to make sure to say some things about Felice. And one side is her amazing professional accomplishments, and then the other side is the secret stories that I think she's okay if I tell you some of them. So I'm not going to take too long, and I'll just tell you that presently Felice is a research scientist at MIT, and she also is supported there by the mechanical engineering department. And before that, she was affiliated with Harvard, both in systems biology at the medical school and here at an enterprise where I got to work very closely with Felice, this initiative in innovative computing. But it's the story before that and before I ever met Felice that I think is really fascinating. So I'm going to skip all of her amazing accomplishments and articles in Wired magazine and accolades from National Geographic, and you can go read this. She's amazing, okay? AAAS fellow, Guggenheim fellow. Let's figure, just the rest of it, okay? Just fill in the blanks, okay? But here's the real story. Imagine you're driving down Route 2. Most of you know where that is, right? And you're listening to NPR. You're listening to Science Friday. And on Science Friday, and I wrote down the date, because that's the kind of stuff I don't remember. It was September 27th, 2002, that Felice changed my life. And she doesn't even know that, because she's like, I didn't know you in 2002, Alyssa. And so the reason is because imagine Science Friday trying to have an episode called Scientific Photography on the radio. So Felice is on the radio with David Malin, who's a very famous, not computer science professor here by the same name, but a different David Malin, who's a famous astronomy photographer who I had heard of. And so I'm listening to David Malin, and he's talking about very large things. And then there's this woman talking about very small things and taking pictures of very small things. And I'm listening, like, this is amazing. Who is this woman? It was one of these things where I, come in the middle. And I hear, thank you, Ira Flato, this is Felice Frankel of I don't know of what in 2002. I don't know. I think of her new book, Envisioning Science, at that point. And I thought, oh, wow, I wonder if I could meet this woman someday. And then by complete luck, the science media group here that's part of the science education department at the Center for Astrophysics, which Phil Sadler, who's up there, runs, had Felice as a guest speaker. And I saw the name and I said, oh, I must go to that. So I go to this talk. And I was so enthralled, as you will be tonight, with Felice's passion for making sure that people understand science. And I think that's really what Felice is about. She wants to understand science, but she wants you to understand, and she wants you to understand whether you're a member of the general interested public or, importantly, whether you're a scientist who has to communicate what you do in science with other scientists, with yourself, with people in your research group. And I think Felice and I share an opinion that a lot of people don't spend enough time really trying to make visual representations of their science that explains the most that they possibly can to themselves and to others. And that's what I was so impressed with such a long time ago. And so I was just gobsmacked by Felice's talk, and I asked her some question, and then I went away, and I thought, well, I'll probably never see her again. And then I went out into the parking lot, and they were located up next to A Street Frames on Concord Avenue at the time. And I had a scroll that I was getting framed that actually my daughter, who was then about 4 or 5 years old, had painted at summer camp. And she sees me walking across the parking lot, and she goes, "What's that?" And I said, because I'm, carrying a canvas scroll, I guess it looked intriguing. And I unroll this very big, very colorful canvas, and she makes this gasping noise that if you get to know Felice, you'll hear a lot of, like, "Oh, this is amazing." It's usually about science, but this was about an image. And we became friends based on that encounter and me telling her about my daughter and her paintings. And then eventually I had the opportunity to invite Felice to join Harvard for this initiative in innovative computing. And people thought, why are you getting a scientific photographer to come to the initiative in innovative computing? And you will see why tonight, because if you really want to represent the most sophisticated science using technological tools or otherwise, you need somebody like Felice to do that translation. And last but not least, I just want to tell you about some of the educational programs that I've seen Felice be involved with. One of them was called Image and Meaning, and it was held at the one that I attended that I remember the most. There were several, but was at the Getty Museum. And what she does is things like bring together, the editor of Nature with science illustrators, with scientists, with writers from magazines, and sits them down in a room and gives them a bunch of crayons and feathers and yarn and stuff like that and says, now make representations of your science till all of you understand. It's a little bit more complicated. Her procedure's a little more systematic than that, but it's kind of like that, okay? So Felice can do everything from crayons to, amazing microscopic imagery. And Felice, there's only really one of you, and so you are all in for a tremendous treat. And I have to say that Felice also told me that her book was really special as she was working on it for the last many years. And many of you will know that Felice has many books, and none of them are good for weightlifting the way that this one is. And that's because Felice, even though she's clearly still going, has put her life's work so far into one book. And so I think that's what she's going to talk about tonight, and I highly recommend that you check out the book afterwards. So thanks, Felice.
Okay. It's kind of wonderful having a friend like this person. I have to say, Alyssa has quite a remarkable career herself, and to have somebody from a completely different world of astronomy to understand what I'm trying to do, it's a gift, and thank you for all of it, and there's much more. So thank you all for coming. My goodness, I was terrified that only a few people will come to the, no, I was telling some friends, why did they put me in this big hall, All right, I'm going to try to make a case to you about what I think is essential in research. If you're not a researcher, that's okay. I want you to understand my thinking as well, because I think it all comes together, or it should. And the case that I'm going to try to make to you, and I try to make on my campus as well, is that making representations is more than making pretty pictures. It's much deeper than that if you take it seriously. And the idea for me on my campus and when I was here as well is to get researchers to understand that the representation is a representation. It's not the thing itself. And that you have to make decisions about how you're going to make that representation. It is an intellectual process. You have to start critically thinking about how you're going to show your work. And in my opinion, it should be part of the curriculum, but that's a whole other conversation. So look at Alice's, can we get the lights down? I did, after all, I'm a photographer, and photographers are control freaks, and there we go. And please don't go to sleep, and if you do, just don't snore. Okay, so Alice is fabricating material in mechanical engineering. She's emulating a sea otter fur, and this is the picture. They're studying insulation and heat transfer. This is the picture that Alice made of her stuff, which she made. This is the picture I made. Oh, good. If you didn't get it, I'd be in deep trouble. So, no, all I did, it's the same thing. I just took it, I folded it, I lit it. Lighting is essential in photography. How many of you make pictures with a real camera? Okay, a lot of you. So then you understand about aperture settings and depth of field. I couldn't get everything in focus, and so I took a series of still pictures at different focal planes and had the software stitch it together. This is an old technique. It's called stacking. And this is how confocal microscopy works. Takes pictures at different focal planes and stitches it. So this is really about getting more than good enough images. Here's another picture that somebody made. I'm sorry I don't have his name or her name. This is material called ferrofluid. Ferrofluid is a suspension of small iron particles in oil. So when you address a magnet to it, you're creating a magnetic field, and it has some interesting things that happen. This is that picture that this person made, and this is the picture I made of the identical stuff. It is an old picture. I still show it because a lot of people still like it. I'm getting tired of it, but it's making a point. And here you're seeing this glob, it's a very technical term, a glob of about 2 centimeters across of ferrofluid that I put on a glass slide. Under the glass slide is a yellow Post-it, also very high tech. And then you have 7 circular magnets under the Post-it. And you're seeing that the ferrofluid responding to the magnetic field. If you look carefully, you could see the window pane from where the daylight was coming from. I'm just using available light. I did hold a green card over it because I wanted to add some sort of color. And if you look carefully, you could see the example of a very bad photographer because I'm in the picture. I'm at the top, you see the lens, you see the 2 lenses of my 105 macro lens. But the idea with why I took this was for a book that I did with George Whitesides called On the Surface of Things. I'm getting you to look, I hope. And then the best of all worlds would be after you look, then you start asking questions. This is my thing. I want people to see that science can be accessible. And I'm giving you permission to ask questions about it because it's a picture. And we all make pictures and we look at pictures and our society is filled with pictures. And so let's use that gift to attract people to start paying attention to what we're doing. I stuck this in because here I am at Harvard, back again. It all started here in 1991. I was given this incredible mid-career gift. It was called a Loeb Fellowship. At that point, I was an architectural photographer. You're not going to get the whole life story, I promise. But my background is science. That's why I can have conversations up to a point with researchers. But I became a landscape and architectural photographer and was given this fellowship at the Graduate School of Design. I found myself hungry for science. I missed it desperately. I audited every class in this hall and elsewhere. E.O. Wilson, Stephen Jay Gould, and somebody said, you should go to this guy. He's teaching a very interesting course, and he seems very visual. And so I went to this course, and he was clearly very visual. In fact, he was able to draw a 6-foot circle on the blackboard, a perfect circle. I was very impressed with that. And he was also clearly visual in how he represented molecular biology. And so I invited myself after the class to his lab. Remember, I'm in a freshman course, and here I was at that time I was 47, a long time ago. You could do the math. And so I said, I'd like to come to your lab. Would that be okay? He said, yeah, sure. Let me get rid of this woman. So I wound up at Mallincroft and introduced myself to some of the postdocs, and they just got a paper accepted to science. And I looked at their pictures and I said, oh boy, I could help them. They needed big time. And that's where it all began. So this is the image that they made of something called a self-assembled monolayer. They're creating hydrophobic and hydrophilic areas on this gold surface. And they dropped water on the surface, and the water stops at the hydrophobic lines that was etched out. Those lines that are creating this design are hydrophobic, so that the water stops. So that this is the picture that they made. And the center rectangle, you're seeing about 3 millimeters across, so you get some sense of scale. And this is the way the image was used in science. I said, let me give it a shot, literally. And so I said, you know, what if you give me a more interesting design? How about a 3x3 grid? And what if we colored the water before you place it on the grid? Because I was thinking aesthetically, but I also had another idea in mind. Because you see, the science here is that the hydrophobic line prevents the water from blending together, which you believe, because they say that in the caption, but in my picture, you are seeing that, by the way, you're seeing the etched line is making it hydrophobic. You're seeing that the water is not blending together. We colored the water with fluorescing dye. I didn't particularly like this. I moved the camera. See ever so slightly what happens when you move your camera, you change the whole picture. And I was getting excited because I thought, oh my gosh, I see science on top. You know, I was already composing it for the cover. But something very important happened. By the way, those rectangles are about 3 millimeters across. I'm using a 105 macro lens. And you know, I'm not crazy about blue and green, but that's all we had, fluorescing material. And the editors came back and said, this is not going to work because we're seeing a duality of the green and duality of the blue, and you're adding something that has nothing to do with the science. I wasn't adding anything. It's just the way it responded to the light. But this was very important. I was very lucky. This is about being lucky, which is everything in life. Not only was I lucky about this comment, but I was lucky that this person happened to be George Whitesides, who, by the way, is pretty well known on this campus and elsewhere. And he, when I go to the next slide, he said to me, Felice, no one is doing this. Stay with this. And I did. And I will be eternally grateful to him. And I stayed with it. But to get back to this little story is the editors felt it was misinformational. And so I went back, and this is the picture that I eventually made, which is cleaner. Again, you're seeing 3 to 4 millimeter squares. They call it the chiclet cover. Those, just to remind you that that's the difference between theirs and mine. And yes, I'm showing off a little bit, but yeah. And so, okay, so here's the thing. Not only, in my opinion, am I communicating to you the science, because you are seeing that those hydrophobic lines are preventing the waters from blending together. That was the beginning of something called soft lithography from many years ago. But I'm communicating that to you, but I'm also bringing attention to the work. This is one of the points that I'm trying to make. This is making a case that we should be making pictures that are honest and real, and we'll get to that in a moment, but they are helping to bring attention to your science because you deserve it, because the science is exciting and wonderful, and why not help bring attention? I'm going to pass through a few of these. This is just from a couple of weeks ago. Now, Bob Langer, they're doing amazing things. They always do amazing things. This is a picture I made very, very quickly. Look at this, the New York Times, NPR, Wired, Scientific American, ABC. I'm not just showing off, I'm making a point. Washington Post, Time. They all are about looking at the science because the picture happens to be interesting. It's not stunningly beautiful. I am convinced that, yes, he would have gotten the attention, but the picture has helped. This was crazy to get this kind of coverage. And he even admits that it could be that the picture helped. And so why not, why not get covers? And yes, I have to tell you real fast, yes, these are all covers that I've gotten, but I thought that by now, researchers are not interested in getting covers because everyone reads the articles digitally now, and the covers are so small, you see thumbnails. It turns out getting a cover brings attention. Journalists, if they see you on a cover, they'll pay more attention maybe to your article and maybe cover it more. I mean, am I being crude here? Maybe, but I'm trying to sell science. I'm not embarrassed that that's my job. I am selling science. And why not get the scientist to help selling it as well? I also am this is a harder sell, but it is absolutely a means of clarifying your own thinking, making your pictures or graphics or more accessible and readable clarifies your thinking in your science. For example, the way it works on campus is I sit down with researchers and we look at their figures. And this was the first iteration, and I'm saying, oh my God, I mean, do I really want to even look at this? And it goes back and forth. Do you really need this? Do you really need this? Eventually, Vera and I landed on this. It's a simpler figure. It's more readable. And you will, I hope, maybe stop at that page in your journal when you're reading it. But in the process of making this figure, you have clarified in your own mind the essential pieces. I feel that this whole exercise of making all sorts of representations should be collaborative. This is what we're doing on campus. We get together, we look at each other's figures or images. We don't totally trash them, but we do say, maybe if you put this over here and do you really need this? It's a very exciting means of getting various disciplines to talk to each other and not judge your science, but just to sort of see what else is going on in your lab. For example, this is something that was in a book that I did with Angela DePace. This researcher you're seeing two visualizations of two explosions. Visualization means that there are actually numbers that they have culled, which has become a visual through software. You don't see this. These are just numbers translated into visuals. And they wanted us to compare the outlined area on top and the outlined area on the bottom. That's what they wanted us to see. And we're saying, help us look, please. Get rid of some of the color, for God's sake. This is something that I see a lot. Color is overused with most of the young people. It's crazy. Here, we're saying, this is what we do in these master classes. We tear things apart and make some suggestions. The overuse of color is something that I don't know what to do about. Or when you have these kinds of illustrations, maybe simplify it by layering it. Now, you can't do that in all your work, but try to edit down your figure to a more accessible approach so people could want to read it. And we also raise questions about the standards that other people have set. When I spoke to Caroline Ross about her atomic force microscopic images, I said, Caroline, why are you perpetuating ugly? Because why, in AFM, atomic force microscopy, it's all rust. Some computer scientists decided to make the default rust. And I say, why? It's basically grayscale with a tint. So get rid of it. But Caroline said something important to me. She said, Felice, when you read an article and when you see a rust image, you know it's an atomic force microscopic image. I'm not going to argue with that, but it's something that, it's a whole issue of talking to each other about how the rules have been perpetuated, and is it the best way to show your data? It's very exciting when we intersect design students, science, and engineering students. Here we have GSD students from Harvard talking to chemistry students from MIT. This was a Picturing to Learn program, which I'll mention in a moment. We brought it into teachers. These are high school teachers working together on how to represent your work is a very powerful tool, not only to communicate to others, but to teach each other what the science is, to make it more accessible. We brought it to Harlem. And these are science teachers that are trying to work together and teach each other the science of what it is that they're trying to teach the students. Picturing to Learn was a wonderful program, an NSF program that we ran for 4 years, 5 universities. We had students draw as if you were explaining to a high school student. That was one of the exercises. This is from Harvard, but by the way, the Harvard students had a lot more text than the MIT students. I don't exactly know what that means. Here's an insulator, a metaphor of an insulator compared to a conductor. By the way, this whole exercise of metaphors is also a very powerful conversation, because all metaphors eventually fall apart. Here's particle in a box. Brownian motion, which is not right. I mean, not everything is right. If we had more time, I could get some answers. Why do you think this is wrong? But it was incredibly exciting. But in the process, we saw the students' misinterpretation of ideas. This is showing molecules and atoms, just the atoms within the molecule. This was not about atoms. This was about molecular forces. And we saw that this student didn't know what in the world he was talking about. He got the right answer, but he didn't understand it deeply. Having them draw and not use a computer, for example, is very powerful, can be. Yes, I'm being crude here. Making representations that are powerful helps with funding. Why not have your reviewer, if you have an executive summary and you have a graphic that is filled with material that you don't even want to bother reading, how about simplifying it just a little bit so that they land on your visual abstract and that they could understand it and want to read it? Otherwise, you're using up real estate, because every page is real estate when it comes to getting some funding. And finally, not in terms of the talk, but my mission is ultimately this is what it's all about. It is truly about making science accessible to the public. And I'm sorry I had to use that filter because I don't use any other filter, so let me use one. But it really is what my book is about. The reason why I wrote the book is to get scientists to start paying attention to the way they're representing their work so the non-expert can at least take a look at it. Here it is. I hope you enjoy it if you take a look at it. It was a lot of work. MIT Press is an amazing publishing house. If any of you wanted to publish books, you've got to go to them. They did things with this book that were insane, wonderful. So the first chapter, I opened the book up. Believe it or not, I opened it with how to use a flatbed scanner. How many of you have used a flatbed scanner to make a picture of something? Not a document, but something. Okay, so a few of you this is going to be old for you. It is crazy what you could do with a good flatbed scanner, not a crazy expensive one that you can set the resolution. That's the important part here. Stefan Rudik wanted a cover. He got the paper accepted. He brings me into my office this stuff. He said, can we get a cover, Felice? What are you, crazy? I mean, look at this. These are all pieces of material that have different properties, mechanical properties. That was the point behind it. So I start laying these pieces on the scanner. This is a picture that a scanner made. And we eventually got the cover. I colored the background. This took, I am not kidding, this took 45 seconds to take a picture, for the scanner to scan the material. Here, Peter was fabricating these devices. They're 1 centimeter across. They have microneedles that eventually perhaps will be a dressing vaccine. Plopped them on the scanner. Joanna was a long time ago working with Euplectella. She gave me this beautiful 8-inch long animal, and I put it on the scanner, and I put a black cloth over it. Remember, the scanner is scanning from the bottom, so you have to kind of imagine where the black is. This was a 1 gig file that I made. Look what happens when I zoom into the image. I'm not making a new picture. I'm zooming into that 1 gig file. Even further, those fibers are 50 microns across. That's the kind of resolution you can get. Our hair is about 100 microns across. It's quite remarkable. You could put an egg on your scanner. You can put pears. You could put tomatoes. And look at the detail. It's crazy wonderful. And one of my students, we ran a course on edX. He was a crystallographer. He poured a supersaturated solution of sodium chloride on the scanner. He wrote software to tell the scanner to make a picture every 15 seconds, and he then stitched it. You see it nucleating out. He stitched the images together. Not bad. It was fun doing this course. I'll never do it again, but there were 12,000 students. That's a whole other thing. The second chapter is on, so the idea of my having a scanner for the first chapter, I want you to get interested in making pictures and making it easy. And it is easy. It doesn't work all the time. The second chapter is on basics. Now, you would be shocked. Here I am at MIT, the most expensive equipment you all can imagine. And I was fascinated at how little the students know how to use a camera. Very expensive cameras, but they don't know the first thing about aperture, for example. Here I'm showing the differences, what happens when you shoot at f4 as opposed to f32. I call it take two. I find it easier to photograph something if I have 2 of them. I just feel it's easier to compose the picture. And by the way, it shows the ability for you to make more than 1, which is not a bad idea. But you see, what I'm doing here is it's just simpler to just compose an image. I talk about backgrounds. For example, we're growing B. subtilis in a petri dish, and so I took the petri dish, I put it on a blue background, and then I put them both on an orange background. Has nothing to do with the material. I'm just trying to make it a little more interesting. Here, I'm using a CD to suggest the optical qualities of this particular device. But unfortunately, as I'm finding out, the young people don't know what a CD is, so I'm having a little bit of a problem. Here, I'm using the background, they're sketches of their material from this campus. And here, this is watercolor palette. I bought this years ago. I knew someday I was going to use this watercolor palette for something. And sure enough, here I did. You see, I was photographing a drop of water for another book George and I did called No Small Matter. He wanted to talk about what a drop of water is molecularly. And so if you see, it's completely out of focus in the background, which is what I anticipated because I'm using a 105 macro lens. And I knew that that's the background I wanted. If you look carefully, the drop acts as a focusing, a lens. You see it's coming into focus if you look really carefully. That's just tangential, but backgrounds could add something to images as long as they're not crazy. The third chapter is about light. This is a book mostly on photography. So clearly I had to have a chapter, at least a chapter. I should write 2 books on it. And showing how just by moving your light here and there, you're getting new shadows, you could bounce light. It's getting you to look at your material in a way that you would not ordinarily see. This is the same device I just showed you before, and in this situation, I'm using a light table as a light source. I'm not putting it on the light table, I'm using it as a source. And the same device here, I'm trying to get the students to just play around and find your own light in a way. This device I actually put on the scanner, but I'm using the scanner as a light source, not to make the picture. I made the picture with a camera, and so the light was coming from the scanner. I really am pushing the students to really kind of have fun with this. Here's a fishing reel that one of the mechanical engineers is looking at. Look what happens when I simply add a light from above. Incredibly, that's a totally different picture. And here, this is the garbage can in which it was placed. I just was curious, what kind of quality would I get with that fishing reel if I put it in the garbage can? It was fun. Look how simply watch the screen, adding a light changes the entire image. It's about paying attention to this. I talk about direct lighting, diffuse lighting. Here is a PDMS material that has a grating on it that is separating the light into its wavelengths, but you don't see it so carefully. You don't see it so well. So what I did was I held a card in front of the light source and made a shadow, so you can see it better. This was not written anywhere. This was about using your head. This is all logical. We're all self-taught, aren't we? This is just taking the time and just spending it to, frankly, have fun, which is, I hope you see I'm having. Munji Buwendi was working with quantum dots a number of years ago. It's interesting that this is still relevant. I thought I made a really good, what you're seeing is a series of vials with the same material, cadmium selenide. The only difference is the size of the nanocrystals, the quantum dots, nanocrystals, same thing, sort of. So you're seeing the size of the nanocrystals affect what light is reflected under UV. This is excited with UV. I thought I was being very clever with this picture. Show me with your hands, where is the camera relating to the vials? Where is the camera? Above, good. And you probably felt that because you're seeing the air bubbles, which I thought was a clever, subtle addition. They hated it. This is the one they asked me to take. Now, and by the way, this is a photograph that made a cover of a journal that never puts photographs on covers because the photograph is the data. Eventually, they did come around, but it took them 15 years to like that picture. It got me crazy. Chapter 4 is about using phone cameras. Now, the book is based on a course that I talked about. Usually it's the other way around. You write a book and then you make a course. With me, I made the course and wrote the book. In the course, I said, you cannot be serious about taking pictures with your phone. You just have to know that. It's just, you're not going to be able to do it seriously. I've changed my mind. Okay, anyone want to take a guess? This is the chapter opener of chapter 4. Do you want to guess what you're looking at? Did I hear condensation from somebody? It is. I was cooking some colored peppers. And the cover, it was a glass cover. And it was gone in 30 seconds. And that's what you use phone cameras for. Here I was walking along Calm Ave, and for whatever reason, they wrapped a tree with cellophane, and I was just working with somebody who was looking at self-assembly. And so I saw self-assembly going on here. Look at the drops at the seam. They were assembling. Something was guiding them, those drops along the seam. It's a Rorschach test, depending upon what you've been working on. Here, with your camera, by putting some pieces of paper behind the equipment, in 30 seconds, you could get an image and then go into Photoshop and clean up those seams. And you can send this out around to your colleagues to let them see what kind of equipment you're working on. But remember, the problem is file size. This is an image that I made of a Petri dish with the phone camera. Look at it compared to the Petri dish that was scanned on the scanner at a high resolution. Look at the difference in quality of the detail. You just don't get the information that you get with a camera and a scanner. But that's going to change. It's already changing. They probably already have the cameras, but they're waiting for us to buy out the others. So I found this device that is pretty fabulous. I don't know if any of you have tried to use your phone to take microscopic images, and you go crazy trying to get it in at the right place. And this is holding the camera exactly where it needs to be. These are just coffee bubbles doing their thing. But notice the composition. You see I'm keeping the edge of the plate. Just pay attention. I'm just not shooting the bubbles. I'm shooting it in a more interesting way. I was on this amazing science of food trip. This is, I'm trying to get you to make pictures. This is an amazing dish that you see, when you knock on it, you see this amazing stuff that tasted phenomenal. The whole meal was about astronomy and the universe. And so when we ate this cucumber and ginger, whatever it was, I have it written somewhere, when you finally ate it, you saw this. She called it Krypton. But I'm trying, I have a whole thing on how to make food pictures. Do not use your flash, for example. But the idea of including this is that I want you to make pictures. Because the more pictures you make, the better a photographer you're going to be. Chapter 5 is on microscopy. I'm just going to quickly go through these, showing this image, which everybody seems to want a scarf out of, is not very successful, in my opinion, that I made, because you are seeing the light. You're seeing my process. You're looking at two colonies of yeast with different genetic material. They differ genetically. And so you're seeing a wild type and a mutant type. And so we want to show you the difference in the morphology. And you're not seeing it because I think you're paying too much attention to me. And this is a better picture. I'm not an artist. I think it's really important to say that up front. I want you to look at the science. I don't want you to look at me or my process. You could use amazing, see, I use a microscope, but I'm not a microscopist. There are people who study this for years. Here I'm using a technique called Nemarsky differential contrast, which Chris is looking at analyzing material with very, very small wells. And so this is a microscopic image. Here you're looking at a morpho butterfly wing that I took with a macro lens, and here I am using it, scanning electron microscope to show you, which is colored, by the way, because SEMs are grayscale. I'll get to that in a second. But the reason why you're seeing it blue is the structure of the butterfly wing. It's reflecting off blue wavelength. That's why it appears blue. And I did borrow images from a couple of other people because it was important that the reader saw the possibilities of using confocal microscopy. And these are kind of pretty damn beautiful. But also important to know that that's something that you can use in the lab. Chapter 6 is about presenting your work in figures. This is an example. The researcher wanted us to look at the buffer layer. I can't find that buffer layer. Help me find it. Get rid of the color and only keep one color so that you get me to look where you want me to look. Very simple. This is what we do. We go back and forth and simplify. And it's a subtle difference, but I think it works better. And what we say in class, one-on-one, in the book, edit. And by the way, edit. Because you put too much in your pictures. You put too much in your figures. You want to help us look. You have to figure out what you could get rid of. At least there's supplemental material now in journals. It's an important idea. I talk about movement. Watch as I click off a series of still pictures. This is something called the Belousov-Jabotinsky reaction. I took it in Jabotinsky's lab. I was very privileged. So you're seeing a self-oscillating reaction. There's malonic acid to indicate what's going on. And yes, I'm showing you a film. That's what a movie is. It's a series of still pictures. And of course, when we want to see things over time, you want to see movies. But there is something powerful about looking at one moment next to the other as well. So I'm trying to encourage the reader to consider a still picture even when you want to show movement. In this situation, you're seeing a suggestion that this 3D printed material can move. I talk about time. This is somebody else's work. I don't have a lot of other people's stuff. I'm too arrogant. But this is so beautiful. Look at how clever these people were in showing this landscape over time. They used some of Ansel Adams' images, they took some of their own, and they made a collage. And you could kind of get a sense of what this place was and is. And you could figure out to do that in your lab. We talk about scale, that you could show scale and also at the same time show a physical property. You could consider getting rid of those dumb bars down at the bottom of your image and use scale as a design element, clearly, neatly showing how large something is. And if you insist on using that dime, please at least compose it a little more interestingly. Do these things make a difference? I don't know. I think so. I don't have any data, but maybe someday I'll collect some data. I don't think I'm going to do that. But just consider moving it a little further. Here's a subject that I wish we had a whole semester to discuss, the notion of abstracting an idea and creating metaphors. Everybody understands a metaphor. Even a 7-year-old kid. Coming up with the right metaphor is fascinating exercise and very powerful. For the book that George and I did, I forget which one, doesn't matter. This is a CD. And we wanted to explain sort of how a CD works, as an SEM of a CD. So this is a piano player roll, on, off, on, off. The same thing with the inside of a music box that I used for another book. It's the binary language of computers. A music box works that way. The note either rings or it doesn't. Trying to get us to understand some very complicated ideas. In my former life, I told you I was an architectural photographer. Faye Jones created this glorious pavilion in Mississippi. It was so beautiful, you cannot see where the landscape ends and the architecture begins. But not only did he borrow the pine coats in his columns, the detail that I showed here, I had a lot of fun in those former days. Notice how he abstracted the surface of the pine coat. He's not copying it. He's chiseling out the design to suggest the design of the pine coat surface. What he's doing is finding the essential part of the metaphor. And that's not so easy. What is the first thing that you have to suggest should be paid attention to? Here's an old metaphor, right? It's all wrong. There aren't these balls of electrons floating around. It's more like this from Roger Hayward, who's suggesting the probabilistic nature of electrons, and it's much more beautiful. I threw this in because it still speaks to me, maybe because I'm from Brooklyn, New York, but this is a metaphor that I erased for the moment the text. It's from the New York Times. It's right after 9/11. It's called Beginnings, an issue about the next New York. It's beautiful, and I think it works. The idea is to come up with these ideas, maybe not so sad, but in science. It's something that we do in our master classes. Chapter 7, we're almost done, I promise, is a subject we do not talk enough about. Every campus has an office of scientific integrity. I went to our office to get material from them. Nowhere do they talk about image enhancement. They talk about plagiarism and patent blah, blah. There is so much manipulation going on with images because it's so easy to do, and we're not discussing it enough with the future scientists. It's critical to talk about it. People actually think the universe looks like this. Do they say anywhere in this picture that this has been completely color enhanced? You have to dig deeply. Now, there's nothing wrong with it because they're making us look. I mean, I'm doing that when I'm coloring my SEMs, but I always indicate that I have done something to the image. This has been completely color enhanced, and yet people are not aware of it. Here's an example that I made. This is a yeast colony. Watch the screen as I digitally deleted the background. I wanted you to see this amazing morphology. In my opinion, I'm not deleting information. I'm keeping the data. The data in this picture is the morphology of the yeast colony. However, I always indicate if I've done anything. Take this example. These are Proteus colonies. Watch as I digitally cleaned the cracks in the agar. Was I permitted to do that? This is what we talk about. I would never do this for the submission, for the inside of the journal. For a cover, I would consider doing it, always indicating that I've done it. And the same, and we just mentioned Charlie Lieber's wires from years ago I colored, which I always indicate that I've done. But look at this one. These are gels. These are 2 to 3 centimeter long gels that have absorbed fluorescing material. I took this picture on film, F-I-L, okay. What was really interesting and surprising, the film did not capture the orange wavelength in some of these gels that my eye saw and that the researcher knew was orange. This is the digital manipulation of that picture to make it look like what my eye was seeing. The manipulation was more real than the other image. Was this allowed? Long conversation. So finally, we're reaching the end, which is case studies, where I go through step by step how I make final images. These are insulin pancreatic cells that are fluorescing, and this is a complete fabrication. This image doesn't exist. It was made of different pieces. I can't draw, but I do know how to take pictures. And so I put pieces together. Here's another one. I didn't have a macrophage. I bought the rights to this macrophage, did all kinds of weird things, layered it, and did a strange thing here to one of them, because this is a metaphor for saying that this macrophage has been deactivated, so that when the device is placed in the body, the macrophage does not fight against it because it was deactivated. That was the science, and that's another picture that we were lucky about. And here's an ugly picture I made with my phone because I wanted to turn the art director on to using this plastic. I wanted to use this plastic in the picture. And so I sent it to her, and then I took a higher res picture, I put graphene on top. She then came back to me. This was creating a metaphor. This picture is not going to exist in reality. It is a picture that we made together to express the process of remote epitaxy in the presence of graphene. This, I worked closely with the nature people. They did things that I was not capable of doing. But these are all pieces of photographs that I made, and it worked. And finding that metaphor is a very valuable exercise. I am absolutely convinced of it. The last chapter is called the Visual Index, where all the science is, because I don't talk about the science in the book, but the science is pretty important. So all the pictures have thumbnails and references and the researchers that I've had the privilege of working with. And the book is connected to OpenCourseWare, where there are 32 tutorials, which frankly I think they're pretty damn good, and they're short, and I encourage you to go online to take a look. John Berger wrote, "We only see what we look at. To look is an act of choice." My hope is that with my nudging, and you're paying attention too, maybe we could get more people to look at what we're doing in science. Thanks so much.
We have time now for about 10 minutes of question and answer. I'm just going to run this mic around the room. Just raise your hand if you'd like to ask a question.
Early in your talk, you mentioned that you think that color may be used too much in showing underlying numerical gradients, and that you prefer grayscale. I would submit that color, when used properly, would convey more information, because with grayscale, you're limited to 1 degree of freedom, lightness variations. With color, you have lightness, you have hue variations, you have chroma variations, and a properly constructed color map can convey all that and impart more visual information, I would submit, than just lightness alone.
Yes, I can't disagree. I probably was not clear, because I was trying to show the difference between showing a host of primary colors as opposed to the grayscale being in the background. But I agree with you. Properly use, the key is properly use, which ain't so easy. And by the way, that's an issue. Oh, Caroline, hi. It's a problem because that's when we start talking about taste. And I have to hold myself back because I have my own taste, which is the right taste. But, you know, and then what I'm seeing too is also the whole color thing is there's a cultural difference in preferences with color. And we have to take that into consideration. There's no easy answer. I mean, none of this is easy. All I'm trying to do is start the conversation. That's the key. But thank you, you're absolutely right, yeah.
Thank you for your beautiful presentation. It's quite clear that you've done a lot of work in material science and engineering fields, and I wonder where you see applications of this notion in social science and in data presentation in less visually stunning findings.
Well, when Alyssa invited me to be part of the initiative in innovative computing, where mostly everybody was a computer scientist or somebody working, I was considered the analog person. Do you remember you used to call me that? Why did she invite me to be part of this, you know? And it was because I brought in a fresh aesthetic. When I saw the screen with their extraordinary algorithm outputs, I had no idea what I was looking at. And I suggest that every area can be visually exciting, even the social sciences and graphics and tables. And I'd love to see what you're talking about at some point. I think that we should pay attention in all areas.
Felice,
Hi, Joanna.
nice to see you. We work together. It's really nice that you at the end mentioned that there is also scientific integrity and the rules that we're supposed to follow and what is allowed, what is not. So in my research, I always have a big problem with data manipulation and especially image manipulation in presentations of papers. When I review papers, I really need to know what has been done to this, to the image, to the scientific content of what you want to convey. So it was also mentioned that you spend time with science, nature editors and different places where potentially there might be a discussion and changes in the rule, or at least establishing a rule of what is allowed and what is not in scientific presentation. And I'm wondering where that stands. In particular, do we have the rules at Harvard, at MIT, or anywhere else where where these rules are better defined? What do we do with contrast? What do we do with background, and so on?
Yeah, very important what you're asking. So in the book, which I'm plugging again, I went to the literature, and it turns out that nature has given this considerable thought. They have met, and I've met with editors. By the way, if you remember that when I colored those rods orange to match what my eye saw, they said no, absolutely no. When I asked them about the cracks in the agar, then they were starting to think, that might be okay. So nature has given us a great deal of thought and guidelines, which are in my book. Nature has pages of guidelines about exactly what you're talking about. Science has 2 sentences. Cell has 3 sentences. But the bottom line is, it is not discussed enough. And I'm not surprised, because you are always thinking ahead of everyone else. You're talking to these kids, and they're all kids, where, you know, everyone's a kid these days, for me anyway. We have to talk about it. I think the university should have guidelines. I don't think that we should count on the publications. In fact, I tried to get something going on my campus, and it didn't work, but so far, well, I'll try again. but maybe Harvard can start thinking about guidelines in the Office of Scientific Integrity. There should be guidelines, period. Absolutely.
Long walk.
Sorry for the long walk. So a question related to that, which is about scientific integrity or just integrity of photography. A lot of the talk about ethics is about what happens after the photograph is taken, but as you showed us, like in the choice of lighting, in the white balance of your camera, all of these things artificially change the photograph from reality. So I'm curious, like and also what you choose to take a photograph of is also part of the ethical discussion. So I was curious if there are any.
That's really important, what you're raising. So, and that's why I, at the beginning, was saying that these are all representations. The very nature of making a picture, from the very get-go, you're making a manipulation. You're making a decision about what to photograph, how much to include in the frame, when to photograph. To say that we shouldn't be making pictures because that's going, I think you'd agree it's going too far. But the more we educate each other about the fact that making a photograph is a manipulation from the very beginning, gets you to at least put it in its right starting point. It's true that when I held the green card over the ferrofluid, I was adding color that didn't exist without the green card. But was I manipulating the content of that ferrofluid form? I was showing the reflective quality of that. You know, I can argue every picture is a manipulation of some sort, but again, the more we know about how pictures are made, the more we'll understand where the line is. But you're right. We should look at every picture that way.
We have time for a couple final questions.
Felice, where do I find people like you to help me find those excellent images? For example, I work at Harvard School of Engineering, and I don't know if we have our own Felice Frankel.
Yeah, well, there should, you know, I have to tell you, I'm not being coy. I really believe I'm not doing anything that you can't do. I really believe it. That's why I wrote the book. It's about, I don't know what the problem is. I've tried to make a curriculum around this. I get 2 to 3 emails from complete strangers every week. They want to do what I'm doing, and there is no place for them to do it. So let's talk about that. But there are researchers who love to do this. They should go into other people's labs as well and be, visual. What should I call myself today? A visual photojournalist, scientist? I don't know. I don't know what to call it. But it really is about communicating the science. I'm not making art. I have to say that a lot. Yes. Mm-hmm. Better photographer, but it reminds me very much of everything that I post in my friends' Great, great. But are you explaining the science in the Instagram? It depends, but there's also no budget for that. Yeah. So we work on, you continue on doing what we don't. We do it for fun. Yeah. There's no being you or doing your job. Yeah. It's not scalable. But we should have a universal population of people like me who. I see somebody there who's a wonderful photographer. There are people, but there's no organization. So maybe we'll start thinking. One more, and that's it. Yeah.
Hi.
Hi.
Thank you for your talk. So you mentioned you had a background in architecture for photography, and I'm curious how this experience influenced your work in scientific photography.
Oh, that's a great question. Okay, so my background is my undergraduate degree is biology with minor in chemistry. And then I went right into a laboratory. I didn't go to graduate school. I worked at Cancer Research Institute, and then became an architectural photographer. And it was in the architectural photographing experience that I started composing. If you were to see some of my architectural pictures juxtaposed with the images I make now, you would see there's the same voice. It's about creating an organization out of disorder. I like very simple pictures. You see that all my thinking is simple, because I'm simple. I like to reduce the idea pictorially. So most of my architectural pictures look like the science pictures. Thank you for that.
Okay, that's all
Thank
we
you
have time for
so
today.
much. It's
Thank you,
really-
Felice.